Hi there. My name is Eric Matthews. I'm the VP of Sales for BMG LabTech in North America. And the webinar content today is luxury and necessity. What do you need to know to buy a microplate reader? So there's thousands of readers in many labs. I've been involved in installing many of those, and we're here to talk a little bit about what we can do to help you decide what's important when you purchase one. So to go over a little bit of what we'll talk about today, we're going to discuss, what kind of features users might need, what technologies contribute to reader performance, what kind of trade-offs do users need to consider when they're buying a microplate reader, what kind of users need microplate readers, and what considerations are important that might not be obvious to people when they're buying a reader for the first time or maybe the second or third time. So who are you? What kind of people use microplate-based readers? If you're here, you're probably in a few different groups. So many folks are in drug discovery labs who are trying to discover new drugs and care a lot about high throughput and low volumes and good performance. Many of our customers are benchtop R&D users in universities and biotech companies who care about running a variety of different kinds of assays. And there's many folks who care about reading just one application as many times as possible as some sort of upstream or downstream process, perhaps related to next-gen sequencing or DNA quantification. So beyond those core functionalities you care about, many readers can be enhanced with um, multiple features that might make your lab more productive, might make your research easier, or make your assays work better. We're going to discuss some of the choices that make uh, those things work better for you. So briefly, a little bit about BMG. BMG is a German manufacturer of microplate readers. We've been around since more than 30 years. We made the first reader for fluorescence polarization, and we're the first company to put atmosphere control for CO2 and O2 into a reader, and among many others. So we have some credibility, and we've been around for a long time. And we're the only company that is dedicated to producing just microplate readers. BMG has offices all over the world. We have a German headquarters where they're designed and built, and we have offices in the USA, UK, Australia, Japan, and France, as well as distributors all over the globe in hundreds of locations. What we're going to talk about a little bit today is how to choose a microplate reader, and what to consider when you're evaluating. And we're going to go through what the must-haves are, so things that you need to have to perform a good assay, things that you'd like to have, things that you might not know you need that make usability more important, and then soft factors to consider when you're evaluating who to purchase a reader from. One thing we're consider when we help you evaluate what to look for in a plate reader are your must-haves and your nice-haves and the key features that you'll be looking at. So among the most primary methods that are important for nice-to-haves are, what is the primary detection mode you're interested in reading? And once you've considered that, what are the important ways that a plate reader can be used to select different wavelengths and give you the best performance, the method you care about. Once you've evaluated what your primary method might be, we care about helping you decide, what the flexibility is that you need and how that works within the budget that you have. A core thing we're going to evaluate here in this presentation is, what assays do you need to detect and what will you be doing in your microplate reader? Absorbance is the base of the food pyramid for most microplate detection. Together with fluorescence and luminescence, those three methods make up the core of most multifunction microplate methods. Almost all those methods can be used in standalone readers. A reader can be made to read only absorbance, only fluorescence, or only luminescence. And that's what we consider to be a basic multimode reader, one that can read those three methods. So the assays you need to detect are going to determine what kind of microplate microplate reader you will buy. Absorbance assays and fluorescence assays and luminescence assays make up the core functions of a multi-mode plate reader. About 90% of assays use these three methods. Absorbance assays are often called colorimetric assays or spectrophotometry. Many labs that use microplate readers refer to their reader as an ELISA reader or a spec, and in these cases, they're using just absorbance chemistries. Fluorescence is used in a variety of methods, and luminescence and bright detection are often used for reporter genes, cell titer glow, and those sorts of methods. TR, FRET, and alpha technology are advanced assays that often act as ELISA replacements, eliminating wash steps and allowing automation-friendly, labor-saving technologies. Fluorescence polarization is often used to measure, protein-protein interactions, drug binding, and is a little less commonly known and used in advanced reader methods. Wavelength selection is important for any method you might be doing. When light comes from a flash lamp, whether you're doing absorbance or fluorescence, there are many wavelengths emitted from that lamp, and discriminating those wavelengths and sending only the ones you need down to the sample and letting the ones you come off of your sample be the ones you want to detect are critical. So blocking unwanted stray light is important when considering wavelength detection. Choosing the wavelengths you need and as broad as you might need are important. In some cases critical for good performance. If you have unwanted stray light or light that isn't blocked by background light, it increases background noise and affects your limit of detection. And so there are several ways we can discriminate between wavelengths. All of them are important. Filters, monochromators, and spectrometers are the key methods. The first thing we'll discuss are filters. So filters are the oldest and simplest technology used in microplate readers for wavelength discrimination. They only allow specific wavelengths of light to be transmitted. And they're available for almost any commercially available assay or any wavelength. Microscopes use almost only filters to detect fluorescence. Filters are the most efficient way to transmit, light through an optical system. The light path is short. They're efficient in transmitting light at the right wavelengths, and they have good blocking at wavelengths that you don't need. They're easy to integrate into filter cubes that can include dichroic mirrors or other sorts of optics. And the short optical path means they can put into a compact device. Interference filters are the same principle that you might be familiar with when you're walking past a oil slick on a puddle in the pavement, and you see a rainbow being produced by light bouncing through a thin layer of oil or on the top of that surface. And filters can be large, so that if you have a lot of light coming from a sample, you aren't limiting it by putting it through a slit or through a grating and attenuating your light. Typically, filters are more sensitive and less expensive than monochromator-based or tunable instruments, but they also have less flexibility. Another way to discriminate different wavelengths of light is with a conventional monochromator. So gradient-based monochromators have been around for decades. They're often calibrated to work for both absorbance and fluorescence assays, so they're compromised to work between both of those methods. They're a simple technology that adds flexibility, but the complicated light path in a monochromator can result in photon loss and scattered light. And as you broaden the bandpass of a monochromator to let in more light, gradient-based monochromators lose performance on the edges of their bandpass window. So it's hard to get two wavelengths close together that you're trying to measure. So the better they are at blocking light, a gradient-based monochromator becomes worse at transmitting light. For that reason, a lot of assays that might benefit from wavelength discrimination, like BRET, nano-orange protein assays, dual glow luminescence methods, don't really work with a gradient-based monochromator. But because they're old technology, they are not that expensive, and so it's an easy way to add flexibility to a lab that needs to use a lot of different assays. Another kind of monochromator is based upon linear variable filters. So a linear variable filter uses the exact same wavelength discrimination method that a filter uses via interference principles. And so adjusting these slides that contain an infinite array of cut-on and cut-off filters allows users to have the same benefits of efficient light transmission that they get with a filter-based instrument, and the sharp cut-on and cut-off wavelengths they get with a bandpass adjustment, without having to worry about all the gratings and mirrors and complicated light paths that come with a gradient-based monochromator. So better sensitivity. Sensitivity is good enough to be used for luminescence. Broad band passes that don't degrade the light performance or transmission as you're reading it. And a lot of benefits for both fluorescence and luminescence assays. In fact, these kind of monochromators can surpass the performance of some filters in some cases. Another way to measure discriminate between different wavelengths is with a spectrometer. Many folks know spectrometers from telescopes that NASA might use to look at a star to see which absorbance peaks are coming from different wavelengths. They are used in HPLCs, instruments like the nano drop use spectrometers. There's an advantage in using these for a few different reasons. So one is that it allows very rapid collection of light at a full spectrum. If you're measuring spectrometry or absorbance and you want to see 2 or 3 wavelengths, and a machine that has only one wavelength at a time they can detect, you have to read the plate 2 or 3 or 4 times to get multiple wavelengths. If you want to add water detection to see path length correction in your plate, that adds a second or third wavelength to your assay wavelength. And so the spectrometer offers an advantage. You can see a full spectrum quickly and evaluate whether you have interference from other compounds, whether your peaks look good, whether you have products and substrates that are both making sense as you're reading. If you have a common assay like an enzyme assay where you have both a product and a substrate, reading the product at time A and the substrate at time A as well gives you good performance when having to read those two analytes at 2 different times during your test. So why is this important to you? Well, this depends on who you are. If you're a drug discovery lab, you might care mostly about performance and you want filters for high efficiency of transmission, lots of light throughput, low backgrounds, and good blocking of wavelengths you don't need. You care about the best performance in the assays that you're doing. If you're a core facility, you might care about flexibility. You might also want to have the best performance for challenging assays when those come along. You might need an instrument that has both monochromators and filters that can do both of those detection methods. If you're a single purpose lab that only cares about doing one thing, you'll need to have a system that performs well in your key primary area of research, perhaps an ELISA or DNA quantification, and you don't care about having flexibility that comes with a monochromator or other systems like a LEDs or a laser. You'll want to have something you can read that single method over and over again. So as you might understand, these systems, when coming together, come with trade-offs: flexibility, performance, and budget. Engineers say that you can have something fast, you can have it cheap, or you can have it good. You can pick 2 of those things. It's similar with many systems. If you want to have high flexibility and high performance, you might need a system that has lasers, filters, and a monochromator that works well in everything you're doing, but it might add some cost to your budget, and it won't be a budget-friendly device. If you're doing something that is very simple and you don't have much budget, then a system only has filters or only that has LEDs might be the best method for you. In the middle of this triangle are systems that have filters and monochromators, perhaps optional other light sources you can use for advanced methods, and you can pick and choose your trade-offs in the methods we're going to come along in the future of this presentation. So filters are less expensive, but the filters perform well for most methods. Monochromators are flexible, but don't perform well for many methods unless you have an expensive monochromator or an instrument that has monochromator and filters in the same device. So there's many technologies that may be important for your research that you don't know you need them until you talk to someone who is selling you a plate reader. And so we're going to go over what some of these complicated and confusing terms might be related to gain, atmospheric control, well scanning, vertical focusing systems, dispensers for your system, and what crosstalk is and what simultaneous emission is and how that might be useful for you. This might be not important at all and not worth paying for, or something critical for you getting good results. The first thing we'll discuss is gain adjustment. So gain is the voltage applied to your detector. So every instrument that is collecting photons needs a way to detect those photons. And you can detect them in a sensitive way or in a less sensitive way, or maybe in multiple ways in the same test. So every single thermometer or luminometer has something that's called sensitivity or gain or something like that. Anyone has used a machine like this probably has encountered sensitivity settings and been unsure about how to proceed and how to get good results. So it's important to have a detector and instrument that works well for your assay. Using the right sensitivity gives you the best results. Using the wrong one might give you results that don't work at all. Many instruments have a way to do an auto gain, and auto gain is important. Auto gain in some cases might give you results that are slow or that create discontinuities in your data. Enhanced dynamic range is a technology that uses a dedicated chip system to detect and see what's going on in each well in the plate and rapidly decide what performance that should be used at. So it essentially creates a detector that won't saturate. So if you read a really bright well, it uses the appropriate gain for that well, something that is high but not too high, so you can see that well without saturating. If you have a very low signal, enhanced dynamic range will read that signal, that sample, with a high gain, so you can zoom in and resolve it versus your background. It's important almost every method. It's fast enough to be used in flash luminescence. So if you have a luminescent signal that you don't know how bright it's going to get until you inject, EDR is important for making sure you can see that signal, even if you don't know what it might be before you begin reading. You have no way to determine the sensitivity setting of the instrument. If you have low signal, EDR gives you performance where you can see that signal as well as seeing signals that are very bright in the same plate. So getting high gains for low signals and getting low gains for high signals and extending your dynamic range so that any method that might come along is going to work well is important for many users, and EDR makes that helpful. Another advantage of enhanced dynamic range in an instrument like you might be interested in is there's no risk of saturation over a long concentration range or over a long period of time. At the beginning of a test, if all of your samples are low, using sensitivity adjustments at the beginning of the test limits what you can do. You might not know how bright it's going to get until hours have elapsed, or you've gone home for the day to see what has happened to your assay in the night. An EDR setting will automatically adjust your gain during the test so that bright wells stay within range and that dim wells, low wells, are still visible as you're reading. So it's important for kinetic assays where time might become critical. It's important to get it for uniform scaling from day to day. If you run the same test every day and your gain is always changing, you might not notice that your background is jumping around, or your reagents have decayed due to being left out of the freezer for a while. EDR means you're always in the exact same scale. So that a result that is 10,000 on Monday should be 10,000 on Tuesday as well if you're reading the exact same sample. That's an advantage for many users. The key thing for a good auto gain or EDR technology is that it makes assays work better, but by making them work better, it makes the instrument easier to use. So if anybody can walk up and use an instrument, it makes people more confident in their results. They're more likely to get good results. It makes training easier, and it makes the cost of ownership for the instrument lower over the long run. People are not confused. They're not doing things they shouldn't be doing. They get good results without having to think too hard about it. So that's a key thing for almost any lab, whether you're doing your core facility who wants to have users who might not be part of your facility or part of your organization until the very recent past. If you're a single purpose user who wants to do the same thing over and over and over again, getting good consistent results without having to think about settings makes EDR quite useful. Another important usability feature is bottom reading. So most instruments can read plates from the top or the bottom of the plate. Most methods are read from the top of the plate. Since you have an opening in the top of the well in every circumstance, reading from the top of that opening makes the most sense. You get photonic collection, and you get good performance in most assays. However, there are many assays where reading from the bottom of the plate makes sense. If you double the distance between the source of your fluorescence or luminescence, you get 4 times less signal. So being so close to the source of fluorescence or luminescence often gives you a performance advantage. If you have cellular assays where you have adherent cells, reading from the bottom where you're close to the source of those cells and you can excite those cells directly without having to excite through a layer of turbid fluid may give you better performance. If the fluid in your in your well is turbid or cloudy, read from the top might not give you a chance to reach the bottom of those cells. If you have a test where you can't avoid it and you have bubbles, read from the top will give you variability as the light optics sometimes encounter bubbles and sometimes do not. Read from the bottom eliminates that problem because you always have the exact same fluid air interface from the bottom of your plate. If you have a plate where you can't avoid evaporation, it's been in the incubator for 72 hours and you've lost fluid in the corner wells, read from the bottom means you always have the exact same conditions, and the exact same depth in each well. You get better performance and better reliability reading from the bottom if you have evaporation or bubbles. And lastly, if you have condensation or a seal that you can't control, maybe aluminum seal or a lid that's been incubated for a while and has condensation all over it, reading from the bottom means you avoid those issues. So it helps for a lot of assays, adherent cells, long-term kinetic assays. You're not sure what might happen in the future, and it's critical for good performance. Almost any method will benefit from bottom reading. Classically, it's fluorescence with adherent cells. But if you have adherent cells using time resolved fluorescence, alpha technology, FP, or luminescence, bottom reading helps those assays as well and gives users more flexibility if those methods are important to them. Z height adjustments. If as a child you were trying to set a leaf on fire with a magnifying glass, or if you're a mean child, an ant, you know that getting the proper focus on a leaf in that circumstance is important. Getting a lot of light into one spot gives you better results because the intensity of light is focused in one area where you want to measure. And so again, classically, if you have a monolayer of cells, those cells are not distributed vertically in the well. They're all in one location on the bottom of the well. And you like to excite those cells, where they're at, bring the light to them and get good yield from those cells and not excite fluid that you don't have any fluorescence in. If you have cells with low volume, you don't want to illuminate the air above the well and have it blossom down into the bottom where your fluid is. Exciting the bottom of the well uniformly and precisely where your reagent is will give you good results when you have low well volumes. If you have unusual well shapes, Z focus is critical. And if you have an assay that doesn't have a lot of yield, if the floor is challenging, if the concentrations are low, getting intense light in one spot is better than having a lot of light in every spot in the well. You get better yield from dyes and more intensity in challenging assays like time resolved fluorescence, FP, and cells that might have fluorescent proteins in them or they might not. It's also critical for low volume methods like 3 to 4 well plates or 15 36 well plates. Simultaneous dual emission is important for many assays. So many assays emit at more than one wavelength. You excite at one wavelength and get emission at 2 wavelengths, and the ratio from those wavelengths is important for your data. So assays like FRET, BRET, TR FRET, FP, fluorescence polarization, some dual fluor assays, dual glow luminescence reporter genes, some assays where there might be 2 fluorescent proteins in the same cell and you need to see the ratio. All of those benefit from simultaneous dual emission. It helps a lot to have 2 detectors that are identical, see the exact same response from both of them. And when you're doing that, reading 1 wavelength of excitation and measuring 2 wavelengths for emission, you get 3 times they're twice as fast. So it's much faster. But also you get more precision. By reading 2 wavelengths with a single flash, you eliminate flash to flash variation as a concern. And if your fluid is changing in some way, if there's a vibration of the fluid, if there's Brownian motion, if the assay you're measuring slowly decays, measuring wavelength 1 and wavelength 2 the exact same instant gives you much better results than if you read them at time 1 and then maybe a minute later or a second later. You get much better results with simultaneous dual emission. So almost every advanced method benefits from this, but it also adds cost to the instrument by adding additional detection optics. Another important usability feature is atmospheric control. So what kind of folks need atmospheric control? People who are doing cell-based assays, methods where they're reading mammalian cells at 37 degrees at 5% CO2 for more than an hour, benefit from atmospheric control and many times require CO2 control in the reader. Cells often aren't happy if they're left out of the incubator for more than an hour. By putting them into a machine that replicates the conditions of an incubator by making it 37 degrees and making the temperature appropriate and the CO2 level appropriate for those cells, they can be happy for days at a time. You can see GFP expression, cell motility, apoptosis, luminescence changes over a long range. Other people who might benefit from atmospheric control are people who want to initiate apoptosis in a cell by lowering the O2 levels, or people who are doing bacterial growth curves and those cells require low O2 levels. Some cancer research benefits from O2 control as well. Many tumors, so they grow so quickly and have poor vasculature, have quite low levels of available oxygen, and simulating what they have in the unfortunate environment of a tumor makes the research on the minute plate reader work better as well. Many readers that can regulate CO2 and O2 can read 1% down to 1% O2. Typically, a reader that can go down to 0.1% O2 means that it is designed from the ground up to be something that works well with gas regulation and often performs a little bit better for those methods. Well, scanning is a feature that makes many cell-based assays and other non-homogeneous samples work better. By default, most readers, for good reasons, will go to the center of the well and read in that well. And if you have fluid that is homogeneous and your detection samples are homogeneous, there's no reason not to do that. But if you have bubbles in the well, if you have injection artifacts from your liquid handler or from pipetting that cause cells to move away from the center of the well, if you have cells that are not confluent, if you have uneven transfection efficiency, if you have viral plaques or motile cells or neurons that only go to the edges of the cell to grow, or other crazy things that cells do, by reading an orbit, by reading a spiral average and averaging those points across the whole well, you get better results and a better representation of what's going on in the well. If you have something you can't avoid, where bubbles go to the side of your plate or edges of your well, by reading an orbital average or a spiral averaging mode, you can eliminate some of the variability by not taking this one point per well and depending upon that single method. In matrix scan reading mode, a reader can give you a heat map of what's going on in the well. So if you have results that are variable, or you can't avoid having cells that are heterogeneous or other things in the well that might be causing spot-to-spot differences, reading in a matrix scan gives you better results than reading only in the center point, or at least gives you options. Most readers can accommodate reagent dispensers. Reagent dispensers are important for methods where something if you add it externally, it might be over by the time you got around to detecting it, or if the half-life of that detection event is so rapid, maybe the half-life of a minute or less, that you would see different results from well A1 than you would from H12 96 wells later. And so if your assay can accommodate mixing or liquid handling outside of your system, if you have something where you need to see an event immediately after you inject it, dispensers are important. So calcium influx assays, where you want to dispense and watch a calcium release in the cell related to G protein interactions, luciferase assays, chemiluminescence, all those methods require dispensing inside the system. Most instruments will do a good job with this, but if you think that this is important to you, you probably care a little bit about can it read and dispense at the same time. You don't want to have a delay between when you inject and when you measure. Flash luminescence is called flash luminescence for a good reason. You also probably care about being able to add different volumes to different wells. If you want to have a different level of interaction in well A1 than you do in well H12, you can add 1 microliter to well A1 and well 95 microliters to well H12, and have buffer added by pump or two in each well, so the same final volume. So quite useful. Crosstalk is an artifact that shows up in many luminescence and alpha technology reads. So crosstalk happens because light can just shine from a neighboring well into the well you're trying to detect, and you get crosstalk directly into your detector. You also can get crosstalk, across the plate from a long distance well. Light is bounced around inside of maybe a poorly designed microplate reader, or you can get light through the side of a well. If you have a 384 well plate, where the wells are directly neighboring each other, a really bright well might shine light directly into the neighboring well through the plastic in the plate, and you get crosstalk that you can't avoid that way. So it's important for many tests that you eliminate crosstalk or correct for it or understand what's going on and not try to hide from the method. So why does crosstalk matter? So luminescence assays are great because they often have a very wide dynamic range in the assay. You could have very bright wells and you can have very dim wells. In fact, you can have wells that are in the counts of millions, and you can have dim wells neighboring them that are in the counts approaching 0 or 100 or 200. If you'd like to discriminate between wells that have counts of 100 or 1 and counts of 100 and 1,000 in the same plate, as as wells that might have counts in the millions, it's important you understand that crosstalk is an issue and you have a way to deal with it. So 8-figure counts next to a well that has counts in single digits or even 3 digits. Crosstalk of 0.2% might seem quite low. Means you have counts of maybe 16 million or 16,000 or 10,000 in wells that neighbor very bright wells. And if you have a well, it should be 1,000 and it's reading 16,000. That's an artifact that you can't ignore, and it makes it impossible to know whether you have you know you know no activity or high activity or moderate activity in that well. Most instruments have a way to correct for crosstalk. So the simplest way is to design your instrument so that the lens is collecting it, doesn't collecting light, doesn't see the neighboring wells. That does a great deal to affect how much crosstalk you see. And almost any well that has a focusing system is good at reducing crosstalk a little bit. However, optical path design is not the only thing you can do by having an aperture or a mask between neighboring wells and the well you need. Blocking light from those wells gives you much lower crosstalk, better CVs, less variability, a better assay window, and better data quality in general. There's assays you can't do unless you have a way to prevent crosstalk from entering into wells that you're measuring. There's also a way that we can design or normalize a plate by using an algorithmic method to see where you're getting crosstalk and measure that directly and use mathematics to subtract crosstalk from a high well into a neighboring low well. Every instrument that you have needs software. Unless you have an instrument that's quite old that uses a thermal printer or a dot matrix printer to give you your data, your plate reader will be giving you data that in electronic format you can access on your computer or your phone or something like that. A reader without software is basically a brick. So bad software limits what you can do. So even a well-designed instrument with poorly designed software will make it frustrating to use and hard to use, and will affect your data quality and how fast grad students can publish or how fast drugs can get to market from a pharma or a biotech company. So good software enables all the features that we've discussed. It nudges users into the right direction by making smart choices and trying to hide choices that are more advanced than they need. So making it easy to use and adding depth to the software where necessary. The cost of software should be reasonable. I think that if you have an instrument where the software cost is very high, or they're always trying to work to get you to buy software that you already have, that's perhaps an indication that your reader company is run by accountants and not by scientists, or at least not non-evil scientists, perhaps. So it's an easy way to understand when you're evaluating a reader what kind of instrument you're dealing with, what kind of company has been making your microplate reader. Control software is the only kind of software you need to think about, but also data analysis software. So what kind of reduction possibilities are possible? Can you make a standard curve easily? Is there basic representation in the software for doing common evaluations, things that everyone needs to do in almost every lab? So what you want to look for is, are common functions easy to find? Do you need to do 1 or 2 clicks to execute those functions and not browse menus forever to find something that's been hidden? Is basic data reduction available for every kind of basic method? If those questions aren't easy to answer, it probably means that the software for this reader was made by some third party, and not by people who use readers every day or communicate with people making the software directly. Data security. So who are you? If you're a QC lab or a manufacturing facility, someone who's using a microplate reader to produce compounds that are going to be sent to users, patients, people that you don't know, it's really important and really critical to have good data security. So software that complies with FDA CFR 21 Part 11, Data can be signed, they can't be manipulated. It's easy to share with people without having the data being accessed by a third party. It's becoming more and more important in all kinds of labs. And if these features are easy to implement, if they're easily available, if they're not expensive to buy, it means that the software people who are working with your plate reader company, understand that all users will need this at some level. It's a sign of a quality reader. Data export. Only the worst data isn't exported from your reader. Almost all data will be sent to another computer via Excel, to a colleague, perhaps to Nature for publication. So looking at your reader software when you're evaluating a reader, is it easy to export data to Excel? Does it take one click, or you have to browse many menus to find it? Can you also export data as a CSV, a DAT, or a text file, or any other ASCII format quickly? Is the database easy to manage? Is it easy to integrate this data management software with network drives or other interfaces that maybe an automated system can send data to a third party or to some other analysis package without having to get IT involved? This is important for most labs, and most good readers can do this quite easily. Automation is a concern for all kinds of labs. If you have more plates than you can read, even 4 or 5 plates that take a long time to read might involve standing around for quite a long time. So does the plate reader integrate with a stacker? Does it have integrated barcode readers? That's a sign that it's been meant to be automated from the ground up. Is the plate accessible to robots? Do you have an easy way to access a microplate carrier if you're integrating with a robot? Does the company you're working with integrate easily with a variety of different microplate liquid handling arms? And do people have availability of app notes and references for automation companies? If someone says they can be automated, but they don't have any instances of the instrument being automated, it's likely that it'll be a challenge to do that, and people have not worked at that company before. So knowing that a company like one of the ones on this slide here has integrated this reader many times in the past is an advantage, and something to be considered. There are a variety of soft factors to consider when looking at a plate reader. The ones that you can't tell by looking at a brochure, by talking to someone, or by even perhaps talking to customers. So how do you interact with people that the company that makes your equipment is something that that matters a lot. If you call the company, who do you get? Do you get someone who knows about plate readers, or do you get an operator who needs to direct you to some place that may or may not even make plate readers themselves? And so this is true for all equipment, especially true for microplate readers, where there aren't that many any longer independent microplate reader companies. So some of these soft factors, where is it made? Is the instrument built at the same place where it's designed? If you're Apple, it's quite easy to have good quality control in manufacturing, no matter where you're making your iPhones. For most instruments, being close to engineers when there's an issue in production means you're going to have better data quality and a consistent product from lot to lot and instrument to instrument. If the instrument is designed in place A and built in place B, it probably means it's designed in a way that can be assembled by people who don't know much about microplate readers. It's going to be less robust, more likely to have errors you don't understand, and harder to fix over time because it's not produced by people who understand how it is being made. Is the machine fiberglass or plastic? What is it made of? So if you see two of the same machines sitting side by side, do the doors close in the same way? Do the doors open in the same way? Do they look the same when it comes to fit and finish? This makes a difference in all things that you might buy, but especially in microplate readers, it should look identical from lot to lot. Other ways, so customer support. So when you're evaluating a reader, you can call the company you're considering and say that you're borrowing a reader and looking for support. Does the person that you are calling understand what that issue is and what you're talking about without needing a product number and to transfer you to somebody else? That's an indication that you are getting good support from the company that you're buying your reader from. Do they read from a script when you call? Do they know what you're talking about without having to explain what a microplate reader is? That's an indication that the company you're working with understands readers at their core. Software. So is it easy to install software for your reader? Is your reader linked to a specific PC that you can't control? Are there extra costs involved with using software in a basic way? If you need to be charged to add basic functions, if the company you're working with is trying to sell you software that you don't think you need, if installing the software on more than one or two PCs becomes expensive, it's clear that the company you're working with sees them not as a collaborator with you, but you as a way that they can get data and money from the instrument after it's been sold. So look closely at the features around the reader that you may have to buy shortly after you buy it, just to make usability. And if you think the company you're working with is trying to introduce friction into your usability, it's a sign that they perhaps have lost their way and not trying to help customers use their readers, but see their customers the way that they can extract value from them. Upgrades, service and support. Ask to talk to a service person if you're evaluating a reader. If you can talk to the person and they can answer questions about what it's like to have an instrument upgraded, what kind of service options are available, how it's constructed, there's no reason that can't happen at any company, whether it's a reader or a freezer. So please feel free to do that. That's a good way to evaluate what's going on in the company and what we'll be dealing with after you've been your reader has been installed and you've been trained. Lastly on this topic, so are there packages available for you to purchase or buy or evaluate? Can you get qualification for installation or operation quite easily? Can you contract with the company you're working with to come in and have regular service, a PM done or a QC done? Can they stop in and see you when you're in your lab? If that's the case, there's someone who's probably dedicated with your reader and understands how it will work once you've bought it, and they care about support for you. And if that's not something they can do, it may be a sign that they have a product that is not important to their business. You want someone who can cares about readers and cares about you as a customer, even after you've been trained and had the reader installed. That's the end of my prepared remarks and slides. This time we'll talk about questions you may have or things that I've said perhaps too quickly or glossed over. Again, I'm Eric Matthews with BMG, and thanks for coming by.